Thank you very much. Now I want to talk a little bit about my work in the digital signal processing of the detection of noise disturbance in the ENAMS system. We call it in German ENAMS. And I'm not quite sure how to pronounce it in English, but I will let it in ENAMS. Hello, Stefan. Problem is to measure the spectrum between 0.05 or 60 megahertz, and you can see one spectrum which is obtained from an antenna system in Bremen at my university. And you'll find, well, this is a lot of signals and they are reducing down to 30 megahertz, and here we have some other signals but we are not sure where they are coming from. And well, the main important thing is to know what is between 0 and 30 megahertz. Well, the recommendations of the ITU, the radio recommendations, P372 in version number 13 from 2016-09, is the radio noise should be measured within, as a noise figure within 9 kilohertz bandwidth. And there is a defined antenna, and this is a little bit specific. The antenna is not one antenna, it must grow with the lower of with the lower frequencies. And when you are using a practical antenna, you can't move the antenna length every time you want. You have to use one antenna and you have to calculate the dB microvolts from the obtained dBms with an antenna factor. It should be a defined antenna, and the radio recommendations divide industrial down to quite rural, and here you can see the galactic noise in the range. Well, the 30 megahertz is here, and you see, well, the galactic noise makes some sense when you are in a quite rural surrounding. Then you will have a galactic noise which you can notice with a very good receiver. Well, the question is, what will be our momentary antenna point? Is it like this? Is it in the industrial area? Is it at the rural area or below that? And well, we find some really low noise areas in Germany as well, but the noise, as every shortwave ham knows, is increasing. Some people says, well, it's increasing 1 or 2 decibel per year. And there we think it is a good idea to make this hypothesis to be measured. And the system has the aim to measure it, not to make just a feeling of the noise. Okay, what do we expect from this RF-EMI-Monitor? ENAMS stands for Electrical Noise Area Monitoring System. Okay, you must learn it. I will ask the not at the end of the lesson. Each electrical system has its own limits, which is defined in standards. But there is a big question: what is the superpositioned results of many of these electrical systems? No one asks. Not the Bundesnetzagentur or the other regulation systems. What noise levels could be found in different regions of our country and maybe other countries? Which frequency range is touched? You'll find that several specific equipments only touch one small part of the spectrum up to 30 megahertz. And this should be found in our system. And the next question is, what is a long-term view of man-made noise levels over time? Not only days, hours, as we do with our manual systems in the shack. It should be mentioned for months and years. So our system, what should measure it, must be stable for this time. With the aim of 50 stations in Germany, we will show a geographical-based heat map of noise and dependency over time. This is the aim of the system. Okay, let us have a look. How can we do this? The ENAMS monitor is an idea of DARC-EMI unit, which is headed by Klaus DL6 SES. Well, this is they're responsible for the system. It's an independent standalone system which we expect, but we will have a central server for administration and data collecting. 50 locations are still needed in Germany. 4 are defined until now. A very well-defined radio system is based on SDR. This is one of our ideas to make it with an SDR. Measurement results must be comparable to results of standard measurement procedures which are used by the regulation bureaus, like Bundesnetzagentur or FCC or other regulation bureaus. The standards and recommendations are mainly the CISPR rules, or today it's DIN EN 55000. And while these standards, there's a measurement standard, there are a lot of other standards, then there are standard measurement recommendations to measure noise, radio noise. There are parameters and measurement procedures on HF, VHF, and UHF monitoring receivers and stations, and man-made measurements in the HF range. You see, this is a very old knowledge, and it's thrown together in these regulations. Noise level measurements are done with standard measurement systems. And the measurement system use different bandwidths. Below 150 kilohertz, a 200 hertz bandwidth is needed. Between 150 kilohertz and 30 megahertz, a 9 kilohertz bandwidth is needed. And above 30 megahertz, 120 kilohertz is recommended. Oh, I didn't translate it. It's from German. Well, the switching time from one frequency to the next frequency is a function of the bandwidth. And the noise is weighted by different systems like peak, like mean, RMS, and quasi-peak. And the radio regulations recommends to use RMS and quasi-peak. Impulse measurements are done with the different weighting, and this quasi-peak is from the old time of analog systems. Look here, you find a diode and an RC element with a second R and a second RC element, and this simulates the reaction of a very old analog instrument. And you see, when we have different weighting, mean value, effective value means RMS, quasi-peak value, and the peak value, you find with the pulse frequency different readouts of the instruments. This is very important to know when you measure pulses. Pulses are established by a power supply for laptop or so, which want to make DC voltage for the equipment, and every 20 milliseconds it recommends a little bit current from the network, and this is a small pulse mainly. Conventional measurements up to 30 megahertz are the transient oscillation is assumed to be 0 for the elements. Measurement procedure is from CISPR 1611. Special tuned, one frequency lasts for 1 second. So we have maybe on 841 kilohertz, 1 second, we have 9 kilohertz bandwidth, we measure 1 second. And then we tune the receiver up to 9 kilohertz more. This means 850 kilohertz. You see, well, the next second, and at the end here, we are 4 seconds farther. So we measure, this is the measurement number 86, 87, 88, and so on, and you see it will take a lot of seconds. When you want to measure the range from 65 kilohertz up to 30 megahertz, one measurement takes a time of 3,026 seconds, means around 56 minutes with 9 kilohertz bandwidth. Probably this is not particularly useful for the planned repetitive measurement, since we want to make every 10 minutes another measurement to find out what is the dependency of time. We selected Redpitaya as a standalone system for ENAMS. This system takes a 1 second sample to a RAM disk by using the HD SDR FPGA module from Pavel Demin with a bandwidth of 1.2 megahertz in 1 second. Calculate the power spectrum density with 300 hertz binwise. Store the power spectrum density with this 300 hertz binwidth. Step from a few kilohertz up to 30 megahertz. So you see the 3,000 seconds which we used before are now reduced to 30 megahertz divided by 1.2 megahertz bandwidth in one measurement. So we have 30 seconds for the measurement. This is an improvement by a factor 100. It's a good idea to do this. The repeated measurements can be done with a Unix cron on the system, since Redpitaya is operated with a Unix system, Linux system, sorry. But the results to collect central databases is needed. The results are put into the central database. An SSH remote access is possible, and we use it, that the administrators can have a look in every system which is spread over the country. The opportunity of special FPGA system is planned, but we don't have it at the moment since it's not a must. The first step is to come out to make some measurements. Calculating some more results from the power spectrum density for the total spectrum, it takes about 2 minutes and 30 seconds. We can do a server-side evaluation and make some more calculations. Mean, RMS, peak, hold, quasi-peak, everything can be done when you have the time recording. Calculate for different bandwidths are done by processing classical increasing the bandwidth when you have 300 Hertz. There is a folding operation. Stefan, kannst du mir helfen? Faltung? Faltung auf Englisch? Convolution. Oh, sorry. Sometimes I forget the words. Okay. I will show you the full spectrum which is measured with one of the system, and I have a website now active, and I switch out to the website, and here you see this is a full spectrum. We have different bandwidths at the moment. I will take the web browser a little bit larger. And here you see, this is Plotly. Plotly is a very simple web-oriented library which can be used locally or on a web service. And I use the web service for this approach to show you a little bit more. And we can zoom inside. First, I want to switch off the 25 kilohertz. Oh, no, sorry. The 25 kilohertz is now switched off. I switch off the 9 kilohertz bandwidth and the 2.7 SSB bandwidth. I can switch them again on. Okay, this is for normal purpose. Well, there was a discussion in the EMI IRU1 region what bandwidth should be used. And there's one national team in South Africa which decided to use 25 kilohertz. It is very useful when you have an RTL stick. The RTL stick can be better used with 25 kilohertz, as I have been told. Well, it's not my opinion. You can see that 300 Hertz is a must. 9 kilohertz is too much, but as a standards, want to have 9 kilohertz, well, we can obtain it with convolution with rectangular from the 300 Hertz samples. Okay, I want to show you a little bit more with the zooming. Let us have a look on 7 megahertz. Here. Yeah, it's good attempt. Let us have a closer look on that. What can be seen when we take it out? We see from 6.8 to 7.4 megahertz. And what we see is there is a noise level with the 300 Hertz. And if you want to use, or if you want to find out the noise level measured with 9 kilohertz bandwidth, you see there are a lot of regions which do not show a really noise level with 9 kilohertz. You see, I should improve the zoom a little bit from here. From here to here. you see the 300 Hertz is good, but the CW region is very crowded at the moment. Here you see the FTA channel. And here you see, well, there's some SSB bandwidth in Europe. It's very, very engaged normally. Here you see some of these samples, and this is a radio up to 7.4 kilohertz, megahertz. And you see the 300 hertz is due to the modulation bandwidth of the radio stations, and sometimes they are not channelized, they are lying in the intermediate frequencies between the channels. And you see 300 hertz is not enough to estimate the noise level. So we are thinking at the moment of the minimum of 150 hertz. Okay, I want to go, well, this can be put out to more analysis, and this is just one step. The next step is to find out how can we estimate the noise level. The noise level can be thrown out. Optical, it is very clear. But in the WSPR decoder, I know the one of Steve Franke, he has an idea to just calculate what is the statistics of the signals we measure. He sorted it and then decided we take a level of a few percent, and everything below is a noise level, everything above is signals. And so it calculates the signal-to-noise ratio. But here we want to make a similar adaptation of this to find out the noise level here. This is our optical view, minus 108 decibel. Okay, just back to my foils. Oh. Okay, this is another view. If the web doesn't function, I can show and explain a little bit. Okay, that's fine. How do we obtain these results? We use a short-term FFT with the algorithm of Mr. Welch. The time domain recording is divided into overlapping in time. Windows, we are windowing and multiply the time domain, make an FFT every time, and evaluate all transform parts at once with peak, RMS, and quasi-peak. And when I click on, you will see the first measurement of frequency. It's of time. And you see this is an overlapping of time, of two time samples. And the next, and so on. This is the typical Welch algorithm. The signals recording with ENAMS is measurement in time. Minimum is 1 second. We have a DDS mixer. The digital signal is mixed down to baseband with a bandwidth of 1.2 megahertz. We select the inner part of a 1.04 megahertz. 29 recordings with selected middle frequency, which is adapted, records the frequency up to 30 megahertz. One record consists of 1.2 megasamples for 1 second. As the RAM of the Redpitaya is very limited, and the RAM disk as well is very limited, we take 1.25 megasamples for 1 second. 10 times will be recorded and were collected and then processed to frequency domain. So we delete the recorded time domain and just use the frequency domain. To find out the power spectrum density, there are 2 calculation algorithms. The power spectral density is calculated the voltage RMS to square divided by the bandwidth and the noise power bandwidth of the window. And the amplitude spectral density is spectrum in voltage, but the square root from the frequency and noise power bandwidth. Windowing, there are 30 different window algorithms well known. The aim is to lower the marginal areas after the transformation. The compromise is steep frequency range greater or improve the bandwidth. An example for simple but bad selection is a rectangular in time domain as a window. This results in a sinus x divided by x function in frequency domain. And this is very broad. Better choice will be a Blackman-Harris or a flat top. And I have some foils from DC9ST. This is it is one of his papers. And I throw that out to show what is the difference between leakage and current power. When we have different windows, no window means rectangular, we see that the margins are different. We see down to 100 decibel, the power spectrum is very broad bandwidth here when we have different windows. And a very good window is a flat top window from this point of view, just not to have the margins. But when we have a look closer at the maximum, we see there's one window, the the rectangular window gives the exact power level. On the other hand, the flat top window has a very broad curve and it has a power difference of minus 13 decibel. This means we have to correct the results. The comparison of different windows are summarized in this table. You see the uniform non-window with this coherent gain, with a noise power bandwidth, and with worst case amplitude error. And you see there are different windows, Blackman-Harris and flat top, the lowest one, and you see the difference of the power is around 5. On the other hand, the noise bandwidth is up to 3.77 when the uniform window has a noise power bandwidth of 1. The worst case amplitude error is here up to 4 decibel, and here it's negligible. Limited resolution of the FFT is in the frequency domain. As you can see, when we are exact on this frequency with the FFT, we get a 0 decibel difference between our signal and the results of the FFT. On the other hand, you will find here the difference when the generator is not exactly on the bin. If it's not exactly on the bin, the power is divided to the neighbor bins, and there you have a difference in the absolutely measured level. Just to have all these elements together in an overview for the FFT deviations, it's the process gain, the filter, and the amplitude of window. And you see the leakage, the equivalent noise, bandwidth, and process gain here, and the current power gain and scalloping losses at the top of the measurement. So let us have a look on the oversampling and process gain. The process gain increased dynamic ranges. Let us make an example. The process gain is calculated 10 to multiply with logarithms from sampling rate to bandwidth, 2 times the bandwidth. And when we take it 300 Hertz, 305 Hertz with the ENAMS system and 125 megahertz sampling rate, we gain 53.1 decibel process gain. And this is showing we have the sampling rate half, and we reduce it to the signal bandwidth, and you see the AD quantization noise could be different. We have a little bit more or less. Let us make an example with RMS and Peak with frequency pulses. We have a frequency pulse of a sinus signal, and the sinus signal is shown in yellow here. You see it's all time 0, and there's a very short time where we have this signal with a few cycles of the sinus signal. The sinus signal has 1234 Hertz. The sampling rate is 10 kilohertz, 10 kiloseconds per second, kilo samples per second, sorry. And the window is showing 10 seconds. And the time of the pulse is very short, as you can see, when we make a zoom into it, we see it's about 200 milliseconds long. This means it's 2% of the total time window. As you can see here in the noise, the pulse is not readable. When you have a closer look, you can estimate it here, but if you don't know that it is in there, you don't find it. Well, the results with a window of 1024 samples per segment in 1 millisecond. This means 1 millisecond, and we have 200 windows now going over the 10 seconds. It shows with an overlap of 50%, a maximum from the 97 windows is the median is very low, and it is not included anymore. So the mean value is showing as a reference level 1. The mean value is from here. The mean, the yellow curve, it could be assumed to be here. And the peak value is 50 times larger, and it is expected. During the RMS value is 6 times larger than the mean. The RMS is located here, and the 1234 Hertz could be really good read out from the results. What is the momentary status of the ENAMS project? The momentary status of the ENAMS project is the sensors, the active antennas, are tested and usable. They are now, there are a lot of examples now where they could be placed and we measure them continuous. System case and integration of a power supply is prepared for test phase with 5 systems. We expect the test phase starting in August and it will last 4 to 8 weeks just to find out the first failures in it. Centralized data collection is prepared and tested for some months now. First steps of evaluation and collection data is done. And 4 locations for the system is defined. Still needed are 50 more in Germany. If you think that you will offer a system could be placed in your ground, then please contact Klaus, DL6SES, at DARC.de or call him. The telephone number is published in the club magazine. I want to conclude the environmental EMI could be measured with SDR system. Redpitaya could be used as a standalone system for this measurement system. Different bandwidths are needed for practical assessment. Comparison with radio noise regulation is a must for external argumentation. And demonstration of the principle is fulfilling the requirements from the standards. So I think we have a system which could be used in the future. Thank you very much for your attention, and I'm open for questions.
Any questions?
Why was the frequency range chosen to be from 0 to 70 megahertz or 30 in your case?
Well, for the ENAMS system, there is now the discussion from 50 kilohertz up to 30 megahertz because of the radio regulations, and to argue against the standardization bureaus.
Okay, thank you.
Answer to this, the question?
Any more questions?
How do you correct for losses in cables to the antenna or in using different preamplifiers? Also the shape of the antenna itself, and don't you need in the end to convert to a field strength seen in space?
Yeah, thank you for this question. A very good question. Well, we have a Redpitaya, which is not only a receiver. As you know, it has 2 independent generators with an DA converter. And therefore, we have 2 channels to make a calibration every few moments. The moments at the moment are discussed about 10 minutes. And there is an inside calibration from one channel into the preamp. And there is next a small antenna which uses the sensor 50, 30 meters away as a receiver. And as you remember, we are starting from 50 kilohertz. And there are very well-known transmitters in maybe in Germany there is the time standard DK5HH, and there are a lot of other time standards spread over Europe, and they are transmitting in the very low frequency range, and which this could be measured. And from these measurements, we think that we will find out errors in the antenna. When we calculate the expected amplitude and compare it to a reference level which we measure from other systems. Answered this your question?
Thanks.
Okay, thank you very much.
Can you say a few words about antenna placement? Where should the antennas be placed? How far from a house or so, and at what height? And
Yeah, well, the antenna stands on an aluminium pole, which is 1 meter high, and the antenna has a length of 1 meter. And from the middle of the antenna, the next building must be in a lower angle than 45 degrees. This is not our idea, it's a recommendation from the standard procedures. Yeah. So if you place the antenna on the ground, maybe in the garden, then it should be away from the house and from the roof of the neighbor's house should be less than 45 degrees. Explain the frequency? Yeah? Okay, thank you. Another questions?
We will have a very important difference in the situation caused by 5G. What do you think about 5G? It's not shortwave, I know, but it will be everywhere, and we will have a lot of additional RF power.
That's right, but it is not the focus of the ENAMS system. The ENAMS system is just for the shortwave radio range up to 30 megahertz, and 5G will be around a few gigahertz. Yeah, so we are sorry, but we can extend this system if you think that is a need, or you can do it by yourself.
I hear it.
Okay.
Any more questions? No more questions?
See anyone? No? That's okay. Okay, thank you very much for the discussion, for the recommendation. You are invited to enter this system as well and to get a receiver for free, but to add a local network that this system could give the results to the centralized database that we can measure this all over the next years. The time horizon is about up to 2025. So we will think that the system will be 5 to 6 years in operation.
Okay. Thank you very much, Michael.